Okay, so double check what your T-chart says, compare it to mine. Remember that we're putting a T-chart underneath where we drew the experiment details and wrote our results, and then we said we're leaving some blank space at the bottom because we're going to write a sentence or two explaining what went on. So in this first one, we were testing to see if it mattered about how much heat you give the liquid, if that made it evaporate faster or slower. And we decided that last day of school that we had class that if you increase the heat, it speeds up evaporation. Do you agree with that claim? If you give something more heat, does it make it evaporate faster? Yeah, when we did this, we tested, we put one in the window and one in the shade. Which one evaporated faster? Look back at the data. Which one evaporated faster, Campbell? The window. And how do you know, Campbell, the window went faster? Tell me some numbers. Yeah, so the shade one had 37 milliliters of water, but the window one had 35. So the window one's going faster. Why do you think the window one was evaporating faster? You know, it's been a while, but there's none left in that window one now. Why do you think, Charlotte, the window one is going faster? It was getting more sunlight, which gave it more heat, yes. Now, since we're making a scientific claim, remember in science, when you make a claim, it's not like saying, oh, that's my pencil. A scientific claim is when you say, this is what's happening, and I have some evidence to back it up. Campbell just gave some evidence. JD, you don't look like you're with me. Campbell just gave us some evidence. The evidence to back this up, that more heat makes evaporation go faster, is that the one in the window had 35 milliliters left, but the one in the shade still had 37. So what we want to do is we want to write that down. Okay, so Campbell said that the one in the window had 35, but the one in the shade said 37. So that's the evidence. That's the numbers that we're going to use to back this up. Now, Campbell could have said the one in the window had less water than the one in the shade. That's still evidence. But when you use numbers in your evidence, just like when you use numbers on the paper airplane, remember when you were explaining about the paper airplane features that made it do better or worse? That makes what you're saying much more powerful. So if I've got numbers to go with what I'm saying, whoever reads this is like, oh, they know what they're talking about. They've really got some proof here. So let's write this evidence down. Let's write the one, oh, here we go. The one in the window, oh, this thing, I'll tell you, had 35 milliliters left. But the one in the shade still had 37. And the shade said 37 milliliters left. Now, don't shortcut on this. Because remember, you're going to be writing in a little bit, and you're going to be using this stuff. So if you shortcut here, you're going to actually hurt yourself later on. We made our claim. We said, based on what happened in our experiment, that we know now that heat, increasing the heat, makes evaporation go faster. Here's the evidence to back it up. We use those numbers. Underneath, where I told you to leave a blank area, we're going to explain why. Now, Charlotte got to it a little bit. She said that it had more heat. But my question to you is, why does giving it more heat make evaporation go faster? Talk to your table about that for a second. So tell me, why do you think giving more heat makes it go faster? What's your idea, Lacey?
It's hotter and it's able to go into the air faster.
Well, why does it make it go in the air faster when it gets hotter, though? What do you think? Brantley?
Because it stings when it gets really hot. And, the hotter it gets, the faster it evaporates.
Yeah. Well, let me ask you this. What causes evaporation?
Heat.
Heat. So then once you give it more heat, it's going to go faster, right? Okay. So I want what you all were saying, everybody was right. I just wanted to put more with it. Let's start out by explaining that since heat causes evaporation, comma, then giving it more heat makes evaporation happen faster. Does that make sense? So underneath, we're going to write down the explanation, the why. Since heat causes evaporation, increasing the heat made it happen faster. Now I'll get out of your way in just a second. You know how this projector is. Since heat causes evaporation, comma, increasing the heat made it happen faster. Signal me when you're completely caught up with me. One. Now, go to the next one. What's the next one? Material composition. How did we test that one, material composition? What did we do? Look back at it in parentheses. How did we test that? What did we do, Leah?
Water versus alcohol.
Yes, remember we put water in one container, alcohol in the other, and then let them both sit out. How much water and alcohol did we use? How much did we start out with, Kate? 40 milliliters, yes. And did one of them go faster than the other? Did it make a difference what the material was made out of? Yes. Which one went faster? Which one went faster, Allie? The alcohol went faster, didn't it? Is it fair to say that alcohol evaporates faster than water?
Yes.
Yes, we know that, don't we? We gave both of them 40 milliliters, put them in the same location, same container, and alcohol went faster. Now, I'm going to scroll down a little bit. And underneath on the water versus alcohol one, make your short T-chart. And again, put claim on one side, evidence on the other. And then let's put our claim. We claim that alcohol evaporates faster than water. True?
Yes.
Okay, so let's just write that down. Alcohol, based on our experiment, alcohol evaporates faster than water. Alcohol evaporates faster than water. Look back at your numbers. How do we know alcohol went faster? What's the numbers to back that up? What's our proof? We got to give somebody some numbers here. How do we know alcohol? Look back at your numbers. Some of you aren't looking. Some of you just like looking around the room like, oh, I don't have to worry. Kendall's gonna raise her hand. Look back at your numbers. Get in your mind what you would say if I choose you. How do we know that alcohol goes faster than water? Olivia.
They both started with 40 alcohol, 32,
So does that match up with your data? The alcohol had 32, but the water still had 37. So let's write that down. The alcohol only had 32 milliliters left. But the water still had 37 milliliters left. See when you're caught up with me? When we set this up, I had you predict which one you thought would go faster. And I think a lot of you predicted alcohol would evaporate faster. We've got a lot of experience with alcohol. Remember that virtual where we boiled the mercury in the alcohol? And remember, the alcohol boiled really fast. It was like 56 degrees Celsius. Water's 100. So we had some things to help us understand that. My next question to you, though, we're getting ready to put why. Why does alcohol evaporate so much faster? We talked a little bit about this the other day. What is it about alcohol that makes it easy to evaporate? What do you know about alcohol that makes it easy to evaporate? Talk with your neighbors for a second. So tell me, why do you think alcohol evaporates easier? What is it about alcohol that makes it go quicker? Avery?
I think it's less dense.
It is less dense, but does density have to do with something turning into a gas?
No.
I like how you're using what you know about alcohol, because that's what I need you to do in order to get this. Alexis? Yeah, do you remember we did the penny with the water on the penny?
Yeah.
And remember we put those drops of water and it made that big dome? Because the particles of the water were really strongly attracted to each other. But when we repeated it with alcohol, did we get as big of a dome? No, we didn't get as big of a dome. Because Alexis is right. Water particles are really attracted to each other, almost like tiny magnets. Remember we looked at how one side of the water molecule has a positive charge, the other has a negative. They act like little magnets. And so they pull together really quickly and really strongly. Alcohol, it pulls together some, but not much. Did we talk about Red Rover the other day?
Yeah.
Yeah, remember I used the example of the game Red Rover. If you're playing Red Rover and you've got a team that's mixed with 8th graders and kindergartners, and they call you over and you're trying to try to break through the arms of two of those kids, do you want to try to break through the 2 8th graders or the 2 kindergartners? The kindergartners, because the 8th graders, it's going to be harder to do that, isn't it? You'll get close. We talk about you get clothesline. Oh, it would be very. And trust me, that game is painful and dangerous. That's why we don't play it at school anymore. So the 8th graders, they're like the water. They're pulling together really tight, so you have to use a lot of force to pull them apart. The alcohol is like the kindergartners. You can pull them apart. You have to use some force, but not much. So when the alcohol and the water both got heat the other day, it just took a little bit of heat energy to get the alcohol in the air. The water had to get a lot more energy to get into the air. The reason, we need to write down our explanation. Why does alcohol evaporate so fast? What should we put here? Why does the alcohol evaporate faster? Why does alcohol evaporate faster? Lacey?
Because the particles don't stick together as much.
Yeah, so let's start out by saying that since alcohol's particles are not as strongly attracted to each other as waters are, it takes less energy to get them into the air. Since alcohol's particles aren't as strongly attracted to each other as waters are, it takes less energy to get them into the air. You may be starting to notice why I put these lessons in the order that I did. Notice how we did that boiling mercury and alcohol, and then later we did the alcohol and penny. See how those things helped you on this? So everything's in a specific order, strategic to help you. Okay, so we just did the material proposition. It made a difference what it was made out of, didn't it? Turn to the next one. Someone tell me what the next one is. What is the next one, Maddie?
Container shape.
Yes, the shape of the container. So I'm going to scroll down. And somebody refresh our memory. How did we test that container shape? What did we do to test that? What did we do to test that? Monty?
We use plate and cup.
Yes, and did we got water in both of them?
What?
Did we use water in both of them? And how much did we use? 60 milliliters. Now, look back at what happened. Did it make a difference whether it was in a plate or a cup? Look back at your numbers.
Yes.
Did one of them go faster?
Yes.
Which one went faster? The plates, yes. Tell me the numbers again, because it's been a while. Somebody tell me. Charlotte, what were the numbers? So 57 for the cup and 42 for the plate. Is that what you have? Okay, so let's do claim and evidence again. T-chart.
I haven't finished the other one yet.
I'll let you copy it when we get to lunch there. You're just on the sentence, right? He's on the next one. So, now, which one went faster, did you say?
The plate.
The plate, yes. Why do you think the plate went faster? What's going on there? Why do you think the plate went faster, Brooklyn?
The water's more spread out and more to get out.
Yeah. Now, she said the water is more spread out, but why would the water be more spread out? What do you know about evaporation? It lets you and make you think that if you spread the water out more, it's going to go faster. Why would spreading the water out more make it go faster? Keep going, Brooklyn.
More water shows and more water evaporates. There's more room.
What
There's size on it.
It's not just the room, there's more to it. You're real close. Avery, add to it.
There can be like 1,000 tall thing, and you can fill it up with water, and it can be really long, and the water will be spread out, but no light can hit it, so it will evaporate.
Well, now, they both got the same amount of heat. Remember, they were in the same part of the room. But why the one that was spread out? What do you know about evaporation? Why did the spread out one go faster? Campbell? Well, it is more open. I mean, but the cup one wasn't closed. Chase?
Water on the plate was more thinner than the water in the cup.
Why does that make a difference?
It makes it more easier to evaporate.
Why does that make it easier to evaporate?
So you can get easier.
You're all around it, Mahi.
It's because the water in the plate has a wider area to evaporate, so it can evaporate more than the cup, because the cup only has like
Why does that wider area make it evaporate faster, though?
because it's spread out more
Uh-huh.
on the plate,
Uh-huh.
so it could evaporate on the plate everywhere.
She's knocking at the door. She's right at it. JD?
Because the sun is hitting more of the water than in the cup, because the cup is shaped like this and the plate is flat.
The sun didn't hit either one of them. We had it on the table. Lacey?
It's because it has to hit the top of something.
Why does it have to hit the top?
Because it can't go to it needs to get on the top, on the surface.
Uh-huh.
And so if it's on the plate, it's got more surface area for it to evaporate.
Yeah, where does evaporation happen? At the surface, remember? We talked about running those races, remember, like running like the 5-cracker 4-miler versus a race when you just got 2 or 3 people. You know, if there's like, 3 or 4 people in the race, everybody can get at the start line, and when they shoot the gun off, everybody crosses the start line at the same time. But if you're one of those big races, like a marathon or a 5K or a 4-miler, some people are going to be at the start line when the gun goes off, but you might be 8, 10, 15 rows back, right? And so those rows ahead of you, when they shoot the gun off to start the race, those rows ahead of you, they'll get to go across the starting line before you will. But eventually, after they get out of the way, then you get your chance to go across the starting line, and then you have to try and make up that time, right? And try and catch back up. Same thing with the plate and the cup. With the plate, you took the same amount of water, but you spread it out in a big area. So now you've got a whole bunch of water molecules at the starting line. Versus if you have it in a cup, you just got some, you don't have as many at that top layer. So if you can take that liquid and spread it out so that the top layer is bigger, then those can get out of the way, and then the next layer and the next layer. But if you have it tall and skinny, the top layer's about like that. Just a few at a time can get through. So when we put that at the top, we said that we're testing container shape, but that really wasn't what we were testing. We were testing the amount of what?
Water.
No, not the amount of water. No, not density. No, they got the same amount of heat.
How much? Like how open the container?
What was that word I said it had a bigger what? The plate surface. We were actually testing the surface area. Which one had a bigger surface? The cup or the plate? The plate. So what I want you to do where it says container shape, draw a line through it. Don't mark it out. I want you to be able to see it, but underneath it write surface area, because that's what we were really testing. Does it make a difference how big the surface is when you're changing states? So draw a line through where it says container shape, and then underneath it write surface area. Because that's really what we were testing, the area of the surface. Does a bigger surface evaporate faster or slower than a smaller surface? So, based on our experiment, is it fair to say that a larger surface area makes evaporation go faster? Is that true? Yeah, that plate was getting it, wasn't it? And I remember I said I wanted to test it that day instead of waiting until Friday. I was afraid it would be completely gone on Friday and we wouldn't have anything to measure. Because I've had that happen before. So let's put that claim down that a larger surface area speeds up evaporation. This thing cannot do circular motions fast. A larger surface area speeds up evaporation. A larger surface area speeds up evaporation. Now look back at your numbers. You can be ready with those numbers. What's our evidence? How do we know the large surface area is faster? I have the same three folks killing it. How do we know that the larger surface area is faster? Give me some data. Give me some numbers. Allie.
Because the plate went from 60 to 42 and the cup went from 60 to 57.
Yes, so the plate only had 42 milliliters left, but the cup still had how much? 57. Yes, it's way faster. So let's write that down. Now, the way we've been writing it, we've been saying the plates had this much, the cup had this much, but you could also say how much it evaporated. You could say the plate lost 18 milliliters, but the cup only lost 3 milliliters. But we'll do it the way Allie said for now. So the plate only had how much, Allie?
42 milliliters.
Only had 42 milliliters left. Lordy, Dave, tell me if that's an A. But the cup still had 57?
Yeah.
Thank you. We just talked about the why. We said that the plate went faster because that wide surface area helped it. Why does a wide surface area make evaporation happen faster? What do we know about evaporation? It makes the wide surface area go faster. JD?
Because it has larger surface.
It does, but why does that matter on evaporation?
Because evaporation happens on the surface.
Yes, yes. We need to start out by saying that. Because evaporation happens at the surface, comma, a large surface area lets more water molecules get in the air quicker. You've got more molecules at the surface now. But if you try to put them in a something tall and skinny, not many water molecules are on that top layer. But if you pour the same amount and spread it out like on a cookie sheet or something, now you got a bunch of water molecules at that top level. So let's start out by what JD said. Because evaporation happens at the surface, a wide surface area. I'm going to use the word exposes. Have you heard that word before? It exposes.
Mm-hmm.
So a wide surface area exposes more water particles at the top layer. Causing evaporation to happen faster. I put a comma after layer. Now, signal me when you're completely caught up, and JD, I'll put that other sentence up for you at the end and say, I want to tell you one more thing before we stop today. There you go. Okay, now, look back at your sciences notebook. What's the next one for us to do, boys and girls? Container composition. So that's what the container was made out of. Look back at our numbers really fast so you can be prepared to answer me. Did it make a difference what the container was made out of? Yes or no? Yes, it did make a difference. Okay, let me get back up here.
Are you videoing?
Yes, thank you for reminding me. I went ahead and started it. Oh, good. It's not off track too bad. Yes, so on container composition, it did make a difference. Which one evaporated faster? The aluminum one or the styrofoam one? Which one evaporated faster? The aluminum or the styrofoam one? Which one went faster? Chase. The aluminum one went faster. Tell me those numbers, Chase. 30 and 35. So aluminum, is that what you all have, 30 and 35? So the aluminum one was going quite a bit faster. Why did we say? Why would the aluminum one evaporate faster than the styrofoam? Talk with your table, your people around you like that. Leah, turn on the top.
But it's still.
So tell me, what did you talk about? Why would the aluminum one go faster? I'm hearing lots of different reasons, and these are good. Just take it and we'll get a break. Why would the aluminum one go faster? Campbell. So Campbell said it attracts more heat. Why do you think it attracts more heat, Campbell? What makes you say that? Now, this is not something you can get wrong. For example, the things that you think about science right now, stay with me, they're based off your real life experiences. So what makes you think that aluminum attracts more heat? What is it that in your life that you've ever noticed or seen that makes you think aluminum would do that? would make you think that? What do you think about what Campbell has said, that aluminum attracts more heat? What do you think, Austin?
It's made out of plastic.
Aluminum's made out of plastic?
Well, it's made out of something.
It's not made out of plastic. It's silver and shiny. You can make plastic that way, but not typically. What is aluminum made out of? It's a well, let's clarify that. Aluminum is made out of aluminum. Remember, that's one of the elements. And it is a metal. Remember on the periodic table, we got metals and nonmetals. Aluminum is a metal, okay, and it's just made out of aluminum. So aluminum is a metal. But lots of people would say every year I have kids who say what Campbell just said, that metals attract heat. What do you think about that statement? Do you agree with it? Do you disagree with it? Kelly, what do you think? Yeah, metal, it does get hot. Have you ever noticed that before? If you're outside and there's something metal that's in the sun and you touch it? Yes, it burns. We talked about slides. Did we talk about the old days, the slide? Yes. Back in the day at city school, they had that wonderful, highly dangerous metal slide. That thing was huge. But if you got on it in the summer, you had to hold your legs a certain kind of way because it would scald you. I mean, that thing would get burning hot. Metal things that sit in the sun, you put your hand on them and they feel hot. But what about a plastic slide at the playground? It gets warm, but doesn't get hot like the metal does. So there's a difference there between how metal does with heat and how plastic does with heat. Now, lots of kids phrase it the way Campbell's phrased it. They say that the metal attracts heat. Now, remember, if we say that it attracts it, that means that if heat's nearby, it draws it to it. Is that what's going on? Lacey?
Metal's a conductor, so it traps heat in.
Yeah, now she said it traps it in. Let's fix this right now. This is coming up, we'll study heat coming up pretty soon. Let's talk about conductors. Metals are conductors. Have you heard that word, conductor? So if something's a conductor, what that means is when the heat touches it, it goes right through it. It flows right through it. It goes from one end of it to the other. Have you ever had a metal spoon sitting like in a pot or something on the stove, and then you come back later and you try to pick up the spoon, and it's really hot? Because metal lets heat flow right through it. The heat from the soup or whatever flowed right through the end of that spoon, and when you touch it, yikes, it burns. So metals are conductors. It doesn't mean they attract the heat. That means when the heat touches them, it goes right through it, flows right through it. Styrofoam is a plastic, and it's not a conductor. Now, don't think that if it's not a conductor that the heat can't go through it. The heat still goes through it, but it's hard for it to go through it. If something does a bad job of letting energy go through it, we say it's an insulator. Have you heard that word before? Insulators. So styrofoam is an insulator. The heat got on both of them, but when it went through the styrofoam, it slowed it down. Did we talk about swimming in a regular pool versus maple syrup? Did we talk about maple syrup? Yeah, remember? If you're at the city pool and you're going to swim across the pool the full length, if it's filled with water, you'll be able to get through it pretty quickly, right? Get over there. But if the pool were filled with maple syrup, you can still get across, but it would be really slow. So the maple syrup is like the styrofoam. The heat can go through it, but it goes through it really slow. When you go to the concession stand and they give you hot chocolate, do they put it in a metal cup? No, they put it in a styrofoam cup because styrofoam doesn't let the heat pass through it. Now, back to our experiment. We had an aluminum pan and we had a styrofoam pan. And I heard some people say, oh, one of them had sides. Yes, one of them did have sides, but they weren't that much taller, and the top was still completely open. It was about the same surface when you measured the surface of each one. So that probably didn't affect it much. So we have an aluminum pan and a styrofoam pan or plate. They get heat from the top, they get heat from the side and the bottom. Any heat that's in the room is going to try to flow through that material. When it hits the heat from the top on the styrofoam aluminum, no problem, there's nothing to go through. It starts evaporating the water. But when the heat that comes from the sides or the bottom tries to flow through the styrofoam, it slows it down. And so that water doesn't get the extra heat. But when the heat from the sides and the bottom tries to go through the aluminum pan, it goes right through it. So aluminum pans get heat from the top and from the sides and the bottom. The styrofoam pans get heat from the top, but not much from the sides and the bottom because it doesn't let it go through it. Our claim, is it fair to say that aluminum evaporates water faster than styrofoam? Yeah, so let's make that our claim. Let me go back and make sure I'm putting everybody's the same way. Aluminum evaporates water more quickly than styrofoam. And what's our numbers? What are our numbers to back that up? How do we know aluminum makes it evaporate faster? Tell me some numbers. Now, I'm getting the same 5 folks who are killing it. These same people are, I'm not worried about them a lick, but some of you have not spoken to me the whole time you've been here today. JD.
It says an aluminum pan has 30.
Look at it while you tell me, so you tell me.
And then the styrofoam pan.
So the aluminum had 30, styrofoam had 35. Is that what you have? Okay, let's write that down. The aluminum pan, or aluminium if you're from Britain, the aluminum pan had only 35 milliliters, 30 milliliters left. But the styrofoam one still had 35 milliliters left. Signal maybe you caught up with me? Why does aluminum evaporate faster? We need to say since. We need to start with since. How should we say this? Why did the aluminum evaporate faster? Olivia.
Because it has more heat.
Yeah, it has more, because, and why does it have more heat? Why is more heat in the aluminum one? Because it's and metals are conductors. Nice, orange group, nice, yes. So let's put since aluminum is a conductor, I need to start it that way because that is what this whole explanation hinges on. The fact that aluminum lets heat pass through it. Since aluminum is a conductor, the heat passes through the water more quickly. Since aluminum is a conductor, the heat passes through the water more quickly. Okay, what's the last one? Adding a substance. How did we test that? Do you remember what we did to test that? How did we test that? Kaylee? Yes, so the substance we added to the water was salt. Yes. So we added salt to one of them. And the other one, we left it plain. Did it make a difference as far as how fast? Good grief, look at that. Those of you watching my video, that is not how I write. This thing board's not cooperating. Let everybody, let the world know. Did it make a difference having salt in one of them? Look back at your numbers. Did one of them evaporate faster than the other? Yes. Raise your hand. Someone tell me which one evaporated the fastest. Which one evaporated fastest? Brooklyn. Mhm.
I got fresh.
Yes, the fresh water. Trust me, if you got that dreamy eyed look like you're not paying attention, I'm coming for you, aren't I?
Yeah, it's coming for us.
Yeah, I'm coming for you. So yes, the salt water did slower. Well, tell me the numbers. Look and find the numbers for me. How much did the salt water have, and how much did the fresh water have, Kellen?
Fresh water had 37 milliliters and salt water had 40.
Yeah, salt water didn't lose any, did it?
No, it didn't.
That's crazy. So is it fair to claim that fresh water evaporates faster than salt water? Is that accurate?
Yes.
Yes, let's write that down. Fresh water evaporates faster than salt water. Now, Kellen just told us the numbers. What I want you to do this time is write your own evidence sentence. The fresh water had this much left, but the salt water had this much left. Write your own evidence sentence and signal me. I want to read it. There is more than one way to write this. Yes, most of us wrote it in terms of how much was left, but you could also tell how much was lost. You could say the fresh water evaporated this much, and then the salt water evaporated this much. Olivia, read how you wrote it.
Both started with 40 milliliters, and water lost 3 milliliters, and salt water lost 0.
Did you hear how she said the water lost 3 milliliters, and the salt water lost 0 milliliters. Now, so I'm not going to fill that in the evidence since you did it on your own. Everybody's is going to be different. So now let's talk about the why. I gave you an analogy, a way to think of this. When we talked about a fire drill, do you remember what we said? If we talked about if there were a fire drill here, we could get out of the room pretty quickly. But if the room had holes everywhere, every 2 feet, from floor to ceiling, you could still get out, right? You might have to turn. I know we did. And then, but it would be slower, wouldn't it?
Yeah, we were.
So let's talk about what's going on with fresh water and salt water. When we dissolve salt or sugar in a liquid like water, a solvent like water, what happens is they don't permanently become, it doesn't change it chemically. They just temporarily stick together. Right? And when the water starts to evaporate, it goes into the air because it turns to a gas and it spreads out. Does the salt go into the air? No. Where does the salt end up? In the cup, yes. Remember the Dead Sea? Remember we saw how the salt was being left behind on those rocks and everything, and the water was going into the air? So why is it, do you think, that salt water evaporates slower? Talk to your table first, your neighbors. Why do you think salt water takes longer to evaporate? What's one of your ideas? Chase. Yeah, we were talking about those holes. When you have just regular fresh water, give it some heat, the top layer turns to gas, gets in the air, business as usual. But if you have salt mixed in with it, give it some heat. First, we've got to get the water pulled away from the salt, right? It's got to get around the salt, then get into the air. So that's going to take more energy. Okay, so it's going to take a longer time because first thing we got to do is use the energy to pull the water away from the salt, and it's got to get around the salt and then get into the air. So it slows the whole process down. It takes longer and it takes more energy. So let's put adding salt to the water makes it need more energy to evaporate because the salt's in the way when they try to evaporate. So let's put adding salt to water makes more energy necessary for evaporation. So it took so much energy regular, but if you put salt in it, it's going to take even more energy. Since the salt molecules are in the way. Now, when I get to in the way, I'm going to put that in quotes because that's not really a scientific way to explain it, but it's a good way for us to think of it, to give us an idea of this concept. So adding salt to water makes more energy necessary for evaporation because those salt molecules are in the way. Now, I want to take this principle and apply it to a different state change. We talked about evaporating. Well, let's talk about boiling for a second. Vapor is the slow form of vaporization. Have you ever seen people like boiling water for spaghetti or something and they put salt in the water? Well, there's a couple of reasons for that. One of the things is for flavor, but there's another reason. When you add salt to the water, it changes the amount of energy you need to get it to change states. In the case of evaporation, we had to give it more energy before it turned to gas. Same thing with boiling. If you put salt in your water before you start to boil it, it's going to take it longer to boil. Because now the water is the same thing going on. Those water molecules have to get around the salt, then go into the air when you're boiling it. So normally it would boil at 100 degrees Celsius, 212 Fahrenheit, but now it might be 110 or 220. And now let's think about why you'd want to do that. I made spaghetti last night. If I'm going to cook my noodles, one of the things I want to do is there's a certain amount of time I want them to cook. And if I add salt to the water, that lets my noodles cook in the hot water a little longer before the water boils away into the air. See what I'm saying? So if I put some salt in it, it gives me some extra cooking time because once it starts boiling, I lose my water to the air, right? And so that gives me a little bit longer for the noodles to stay in the water and cook because eventually all that water will boil into the air and we'll have to come back and add water. Another way we use this is in the winter. Have you heard about when they think it's going to snow that they put salt on the roads?
Yeah.
Yes. The reason they do that, a lot of people think, oh, the salt melts the ice. No, that's not what's happening. No. Think about if you ever watched it snow and you saw a snowflake land on the sidewalk. Did you ever see that happen before? Austin, you're not with me. Have you seen that happen before? You don't know what I'm talking about. You totally left me. Have you ever seen watch snow land on the sidewalk or the pavement or something? What does the snow immediately do with plants?
Go away.
It doesn't go away yet.
It melts.
It melts, yes. So as soon as the snow lands, the ground is already warmer than the 32 degrees or the 0 degrees Celsius it needs to be. It melts immediately. Okay. If it's really cold, it might stick around a little bit and then melt. But it starts to melt. When we get a lot of snow, then it'll stick around if it stays cold enough. But it starts to melt, turns back to water. If we have salt on the road, when that snow melts, now you've got salt water. And just like it took more energy to turn it to a gas, you have to remove more energy to turn it to a solid. So if we put salt on the roads, when the snow lands there and melts a little bit and turns to salt water, instead of freezing again at 32 degrees, it gives us a little more time. It might freeze at 26. That gives us a little bit more time that we can drive safely. It keeps that water from freezing back and turning to solid ice and causing wrecks. You see what I'm saying? So adding something changes the temperature that it needs to be at to change states. Normally it boiled at 100, now it might be 105. Normally it froze at 0, now it might be -4. It gives us a little bit more time, and so scientists use these principles to help us come up with ideas of how to make our lives easier. So far, so good?